Okay, now let's move on to our final presentation of today, and it will be by Oliver Gasser, Head of Research at IP-Info, and presentation title is WHEREIS IP Address Registration Geo-Consistency.
Thank you. All right. So, hi everyone, and thanks for staying until the last talk. I try to be quick so that we can then later on get ready for the social event. So yeah, as I said, I will be talking about WHEREIS. This is not only my own work, this is joint work together with Rob Beverly from the San Diego State University and Amrish Fokir from the Internet Society. So what we looked at is IP address registration geoconsistency. So let's get started with some background. As I guess most of you know, the internet resources are being managed by what's called Regional Internet Registries, or RIRs. And the primary role of these RIRs is to manage and distribute those public internet address space within their respective regions. We have 5 RIRs. We have ARIN for the Northern America region. We have LACNIC for the Latin America region. We have the RIPE-NCC for the Europe and Middle Eastern region. And we have AFRINIC for Africa and APNIC for the Asia Pacific region. And the goals, according to RSC 7020 of Internet Numbers Registry, is to facilitate the allocation pool management, because IP addresses are a finite resource, and they need to be they're inherently unique. And the allocation is done hierarchically to facilitate efficiency, and we also, or the registration information should also be accurate to meet operational needs. Now, you might think, okay, great, all is well. Some of you might have seen this before in a talk by Paulius today. I will quickly go over it again. One of the problems that we currently have is what's called the IPv4 address exhaustion. Basically, this means that there are theoretically more than 4 billion IPv4 addresses, but only around 3 billion are currently being used, and those 3 billion obviously is not enough for the needs that we currently have. So as you can see already in 2011 on this timeline here, we see that IANA allocated the last 3/8 address space, and this trend triggered to an allocation of 5 previously reserved /8 address blocks, 1 for each of the RIRs. And as you can see on the timeline, step by step, each of the RIRs started using their last free space. And for example, RIPE-NCC allocated the last 3/22 space in November of 2019. So is it not possible anymore to get any IPv4 addresses from RIRs? Well, it's not impossible, but it's quite challenging, right? So we have the concept of waiting lists for most RIRs. And the idea there is that if you want to have internet IPv4 resources, you need to apply for the waiting list, and then you need to wait a certain period of time. And for the RIRE-region, for example, there are currently more than 900 LIRs on this waiting list, and the average, the current wait time is 1.5 years. And here on the bottom you can see the blue line being the number of LIRs, and the black line the average waiting time in days. So, is there another way of getting IPv4 addresses? Maybe a less legal way, let's say? Yes, there is. You can obviously try to steal IPv4 addresses. The most, or one of the more famous examples are the issues revolving around AFRINIC, who some of you might have heard of, with certain, where a lot of IPv4 addresses have been stolen, and also which led to some, law kind of issues with the law as well, and even led to AFRINIC kind of almost ceasing to exist or running into a bunch of serious operational problems. So if we go back to the figure that I showed you initially, namely the 5 RIRs, what we wondered now is where are those prefixes used after the allocation, so after they have been allocated. So is it really the case that if one prefix is allocated in the RIPE-NCC region, it's also being used afterwards in the RIPE-NCC region, or do we see some inconsistencies there? But before we started the analysis, we looked at the policies of the different RIRs, because RIRs are separate organizations and they can set their own policies. And as you can already see in the table here, the policies are quite disparate, with some RIRs being very or relatively open towards out-of-region use or even out-of-region infrastructure or the ownership, for example, the RIRE-region or the AFRINIC region, whereas other RIRs such as AFRINIC or also ARIN are relatively strict, where it's basically very difficult to legally have out-of-region use, except for some certain exceptions, for example, in the AFRINIC case, if it's for connectivity back to Africa. So how do we want to identify this out-of-region use? And this is where the WHEREIS database comes in. As you know, the WHEREIS database contains a lot of different information. So we have information about domain names, autonomous systems, but also about IP prefixes. And here you can see one example IP prefix, that is the net range here below. And this is a prefix that is from the ARIN region. So the WHEREIS RIR is ARIN. We also have another interesting information, a bit of information here, which is the organization ID. And this links then to another object in the WHEREIS database with information about this organization, where we then suddenly look at the country information, which then says Brazil. So the relevant RIR for Brazil is obviously LACNIC for the Latin America region. So we already see a mismatch here between the WHEREIS RIR, which is ARIN, and the organization RIR, which is LACNIC. But what about the actual location RIR? Because that's what we're also interested in. We want to understand where those resources are actually being geographically used. And that's where RIPE Atlas comes in. Super cool tool managed by the RIPE-NCC. It's basically a globally distributed network of measurement probes. Here on the right side, you can see a map of the probes. Obviously, it's a bit skewed towards the European and maybe North American region, and with less probes in, let's say, Africa and parts of Asia. There are different types of probes. So there are hardware probes and software probes. These hardware and software probes are usually deployed by, let's say, network enthusiasts in their home. And then we also have what's called anchors, which are basically more powerful probes, servers, if you will, that you would put into data centers, and those are then deployed by either the data center or companies and or universities, for example. And RIPE Atlas has a credit-based system to schedule measurements, which means that if you're hosting your own probe, then you get credits for it, and then you can run your own measurements. Well, what we want to do now is to find geo-inconsistent prefixes using RTT measurements and speed of light inference. So the basic idea is if you run multiple RTT measurements, you can then kind of draw a polygon around the possible area where those prefixes or where those IP addresses would be located. And for our study, we conducted multiple measurements per prefix that we analyzed. So we ran measurements from 20 probes for each of the prefixes that we analyzed. And we chose the probes in such a way to cover kind of all, to have a good coverage around the globes. So if, for example, we have a prefix that tells us that the prefix is in the UK, we first run 5 in-country measurements, so from probes within the UK. Then we run 3 additional measurements for each of the RIRs, for each of the 5 RIRs, which makes a total of 20 RIPE atlas measurements for each of the prefix that we're measuring. Right. Now, before I tell you about the results, let me talk a bit about the terminology that we use here. So we have 3 different RIR regions in our analysis. We have the region of the registered RIR prefix. We have the region of the registered organization, and then we have the actual physical location that we measured using RIPE atlas. Now this brings us to a decision tree that you can see here on the right. And just quickly going through the possible outcomes here. If all of those 3 regions align, so if we have the same registration, organization, and geo RIR, we call this a fully geo-consistent prefix. If the RIR region does not align, but the organization and geo RIR aligns, we call this an organizationally geo-consistent prefix. If the organization does not align, we call this an organizationally geo-inconsistent prefix. If the registry, if the geolocation does not align, if the measured geolocation does not align with the RIR region and the RIR organization, we call this registered geo-inconsistent. And if all 3 are different, this is a fully geo-inconsistent prefix. So you can already see that there are different types of inconsistencies depending on those 3 values for the registration, organization, and geo-region. Now let's have a look at our results. So we measured 20% of IPv4 prefixes and 20% of IPv6 prefixes. You might ask, okay, why only 20%? Well, RIPE atlas has certain thresholds and limits, and you cannot run as many measurements as you would like to do. For example, there's like a 100 concurrent measurement limit. So we thought, okay, let's do the 20%. I think that should give us a kind of a good understanding of the overall geo-consistency. And what we can see in this table here is that the vast majority of prefixes that we measured for IPv4 as well as IPv6 are either fully or organizationally geo-consistent. So more, let's say, 99% for, or almost 99% for IPv4 and 89.5% for IPv6. So the first interesting thing might already be IPv6 is not more geo-consistent compared to IPv4, as you can see. And then there are, I would say, a non-negligible number of inconsistent prefixes for IPv4 as well as IPv6. So for IPv4, we have, if you add those up, almost 1%. And for IPv6, we have 1.5%. And we also took anycast into account. So if we identify an anycast prefix, we would not count that as any inconsistency at all. Now the question is are there any differences between the RIRs? And the answer is yes, there are some differences between the RIRs, but remember that the y-axis here starts at 90%, so the y-axis is the percentage. Let me briefly explain the plot. So this is a group bar plot. The left side, or the left bar is always IPv4, the right bar is always IPv6. The shaded regions are the inconsistent categories, and the non-shaded regions are the consistent ones. So you can already see that there are certain regions, such as ARIN or APNIC or AFRINIC, where we find percentage-wise more inconsistencies compared to, for example, LACNIC or the RIPE regions. Right. Now, the next question that we're interested in is where are inconsistent prefixes used? And this on this Sankey diagram, the left or the source side is the location of the prefix in the WHEREIS, and the right side is the location of the physically measured prefix. And you can see that for IPv4 as well as for IPv6, we have a lot of kind of pairs between RIPE and ARIN and RIPE. But this is also just because of the larger number of prefixes that we measure for those two RIRs. And if we look at AFRINIC, for example, which has a very strict out-of-region policy, we see that, for example, the IPv4 prefixes of AFRINIC are mostly used in the APNIC, RIPE, and ARIN regions. Now, you might ask yourself, well, that's all great and cool to know, but yeah, what's the real impact? Like, what is the effect of these geo-inconsistent or out-of-region prefixes? And one of the effects that we analyzed is the effect on IP geolocation databases. So IP geolocation databases, as the name already says, puts a location to an IP address. And those IP geolocation databases, they use a multitude of sources. And one of those sources might also be WHOIS. So if the WHOIS is not actually the location or doesn't display the actual location of this IP address, of the physical location, then of course that leads to problems afterwards. So what we did here is to look at 3 different IP geolocation providers or services, namely MaxMind, IPinfo, and DBIP. And we checked for all of the inconsistent prefixes that we identified. How many of those do those geolocation providers also identify as being inconsistent? So higher number here or higher percentage here is better. And what you can already see here, for AFRINIC, for example, MaxMind is only able to detect less than 20% of the geo-inconsistent prefixes. And if we compare that to IPinfo, we see that it's almost 80%. And DBIP is even lower than MaxMind. And this is pretty consistent across all of the RIR regions, where we see that IPinfo detects many more out-of-region prefixes compared to the other 2 databases that we looked at. Now, what could be possible reasons for this? IPinfo has a probe network. So this is somewhat similar to RIPE Atlas, but it allows us to do many more types of measurements and many more variations of measurements compared to RIPE Atlas, and we don't have kind of the limitations there. It is built up of more than 1,100 globally distributed probes from more than 440 ASs in 135 countries and more than 460 cities. And we do a lot of measurements using this probe network, and this results in more than 300 terabytes of data per month. Here on the right side, you can see a map of the probes that we have currently deployed. And you can also see that we have some quite, let's say, exotic regions or exotic places here, like Mauritius or maybe Malawi. So we're always constantly expanding the probe network. So if you would be interested in, or you could help in hosting a probe in one of your networks or so, it would be great if you can reach out to me and we could talk afterwards. So yes, as I said, IPinfo leverages this probe network to validate geolocation information, and therefore is able to detect many more of those out-of-region prefixes. So we thought to ourselves, what if we use IPinfo's probe network instead of RIPE Atlas to run the WHEREIS approach. So we use the RTT measurement results from IPinfo's probe network, where we target all pingable IP addresses and have used basically the same detection algorithm as we previously did with RIR-region. And as you can see on the right side here, IPinfo detects many more geo-inconsistent IP prefixes. This is especially the case for IPv4, where we detect more than 60 times more inconsistent IPv4 prefixes compared to RIR-region. And this is mostly because we have located our probes we have many more probes compared to what we use in the previous measurements. And also we located our probes in areas to best cover all of the latency or all of the regions to have a low latency for our detection approach. Coming to a close here. So what I've shown you in this presentation is that we looked at geo-inconsistent prefixes and found thousands of those prefixes. We also used IPinfo's probe network, which is then able to detect 60 times more geo-inconsistent prefixes compared to if we were only to use RIR-region. And we also reached out to 3 RIRs to validate our results with them. And we also coordinated with industry, specifically with the leasing provider IPXO, where we've already heard talks about today, who was then able to correct some of the inconsistent prefixes with their customers. That's all from my side. I would be happy if you were to reach out to me via this email address, or if you have any questions, or we can talk offline. Thank you.